shot me down. I thought being able to call my son Little Roman would have been the greatest thing ever. Those who watch the show might know that very inside reference. So I got some of my graduate students into that show, and they hate me for it. Because they'll say something like, hey, do you know what the face of Bo is? Like, that's an old fact. All right, so questions. I actually don't have a copy of the exam because my printer wasn't working 5 minutes ago. All right. And I'll try to keep it here in case you have any extra questions. So the exam is going to go through the aldol reaction. And so I briefly introduced the aldol on Monday. And pretty much that's the extent of the aldol I'll ask. I'll save the more detailed questions for the final. Yes?
Is the only reaction in chapter 16 Wittig?
Well, it's the Wittig, and then there'll be some amine enamine chemistry. Because on exam 2, I really didn't ask much amine enamine chemistry. And so
No.
the idea for that stuff is if you take a carbonyl and so you can take a ketone or an aldehyde and a secondary amine. You get an enamine. Sorry about the confusion with the room. Someone informed me that at 6 o'clock, 1:30 was taken. So I sent an email out last minute.
Professor, the whole thing's gonna be recorded, right?
Yeah, it looks like it is, yeah.
You got to.
I don't know when it will be put up online.
Tonight.
I feel like Indiana Jones. Yeah. You know, Indiana Jones went to Yale? Or Indiana Jones was the real Indiana Jones. Hiram Bigham was a Yale professor in like the 1920s. So the entire museum was completely, Natural History Museum at Yale was completely dedicated to him. And when they shot the new Indiana Jones with Shia LaBeouf, they shot campus down for a week. And so you'd see like Shia LaBeouf and, is that how you say his name? I don't know. I don't remember untalented actors' names, sorry. But you'd see him and Harrison Ford just walking around the campus. So what we're going to start for this exam is imine enamine chemistry. Technically, this was supposed to be an exam 2, but I forgot to put any of these questions on exam 2. And so remember, if you take a ketone or aldehyde and an amine and catalytic acid, you get an enamine with the secondary amine. So secondary amine, you get an enamine. and you take a primary amine, you get an imine out. And the thing about enamines, do enamines remind you of anything we've discussed in chapter 18 or 19? Enols, right? So enamines are a lot like enols. What do you think will be more reactive towards an electrophile, an enamine or an enol? So the double bond of an enamine, do you think will be more or less reactive than the double bond of an enol? More or less? More. So nitrogen is less electronegative than nitrogen, right? Than oxygen. So what that means is, since nitrogen is less electronegative, the lone pair of electrons in the nitrogen can more freely donate into the enamine double bond than in the oxygen, since oxygen is going to hold onto the electrons tighter because it's more electronegative. And so that means there's a lot more partial minus charge on the enamine carbon than in the enol. And so an enamine is more reactive than an enol because it's nitrogen. So we can pretty much do all the chemistry an enol can do. Just to show an example. If you take Br2 and an enamine, you can actually brominate the alpha carbon of an enamine. The thing though is, this isn't stable, right? It's an iminium now. So nitrogen carbon double bond where the nitrogen is disubstituted, we now have an iminium. So it's an imine with a positive charge, iminium. And so if this happens, then what can happen is if you form an iminium in a reaction like this, then you can just throw in water. And via an acetal type mechanism, the water is going to attack, and we're going to have some proton transfers, and eventually what we're going to get out is the carbonyl plus the secondary amine. So again, this is just a hydrolysis of an iminium with water. Do you want me to go over that mechanism?
No.
Yeah, it's similar to the chapter 16 stuff, right?
Yeah.
It's an acetal mechanism. Just water attacking and all the proton transfers and that fun stuff, eventually kicking off the amine. So classic stuff, but just stuff to remember how this works. The other key thing to remember is with imine and enamine chemistry, the formation is completely reversible. So you can take a ketone and a secondary amine and go to your imine. Conversely, if you have an imine, you can throw in water and acid and get your ketone back. So just like acetals, where acetals form reversibly depending on Le Chatelier's theorem, do you have water or alcohol and acid? Imines can form reversibly. So, you know, if you have an imine and then you throw in H3O and water, the product will get out. Once again, just as in this case, will be your ketone back plus your secondary amine, your primary amine, sorry. So it's all reversible. Just like acetal chemistry, you can go either way. And Le Chatelier's determines whether or not you're going to favor the ketone or the acetal. Same thing with amine chemistry. You can, if you have more base and only a little bit of water with the amine, you're going to favor the formation of the imine. Conversely, if you have the imine and you throw in excess water and acid, what you're going to get out is the carbonyl. So if they're completely and utterly reversible. So I could say this plus this goes to this, or conversely I could say here's an imine with water and acid goes to question mark. And with an imine, then the answer is, well, it's going to hydrolyze up to the ketone again through the acetal mechanism, acetally-like mechanism. So it's going to start here, then it's going to go to the Wittig. The Wittig is going, the mechanistic Wittig question will not ask to explain cis or trans, but there will be 3 or 4 tell me the product questions. So I'll give you starting materials, so I'll give you your ketone or aldehyde, and I'll give you your phosphorusylate, and you'll tell me what the product is, particularly if it's going to be the cis or trans. So you don't have to explain, you don't have to draw those 3-dimensional transition states I drew in lecture. However, if your mind works like mine, I wouldn't remember unless I drew the 3-dimensional transition states. It's sad, I know, that I would have to draw the 3-dimensional transition states rather than remembering that an electron donating group will give cis and an electron withdrawing group will give trans. So we'll do the Wittig. And then after that, then we'll go to the next chapter, which was chapter 17. The kind of question I'll ask for chapter 17 was, I'll give you an equilibrium. I'll give you an equilibrium that might look like this. What's up?
So is this going to be on the test for sure?
Yeah.
Okay.
Be familiar with it. I'm not going to say how it's going to be on the test, but knowing this, particularly stuff like this will help. And knowing that enamines can act as good nucleophiles. I didn't cover it in lecture, but I feel like it's a reasonable jump to say enols react like this. Enamines are a lot like enols. So if a enol does it, an enamine will certainly do it. The type of question I'll ask for chapter 17. Well, chapter 17 has 3 parts to it, really. The first is the straight up, nothing special nucleophilic acyl substitution. Actually, let me actually show you the way I would actually put it in the test so you guys are prepared. So I would give you an equilibrium like this. And I would ask you to circle the product that is favored in this equilibrium. So which of these products, the acid chloride or the amide, would be favored in the straight up nucleophilic acyl substitution equilibrium?
The amide.
The amide wins. So that's the type of question I will ask for that part. So which one will do it? And then maybe I'll give you 4 or 5 different ones. And some of them, and then I'll say, please rank as drawn the equilibriums according to increasing K value. Okay? So just to show you another, so I might have something like this, and I might have another equilibrium. So I might give an equilibrium like this. All right, so in this one, which equilibrium is favored?
The left.
This one's favored. So if I gave you these 2 questions, you'd circle the amide for being favored, and you'd circle this one for being favored. And then I might have a question that says, please rank these questions according to the as drawn KEQ. And so how do we do the KEQ? Well, we just, back of the envelope, we just take the pKa from this side. Oh, sorry, we take the pKa of this side and we subtract it from the pKa of this side. And then we do 10 to whatever that number is. So in this case though, the leader group's HCl. So the pKa of HCl is like -4 or something. It's sub-zero. So of course I give you pKa table, so you would go to the pKa table, or you would know it at the top of your head, and say, all right, the pKa of HCl is -3 or something like that. And so this is -3. You know, well, let's just say 0. 0 is going to be easier, and it's not going to change anything. And then the pKa of this guy is about, 10, right? Oh, I guess the pKa of this is 35. All right? And so then, actually I take it back. What you do is you say the pKa of this minus the well, there's two ways you can do it. You can do it of the pKa of the thing that forms the bond minus the pKa of the thing that left. Or you can do it the pKa of the base on the left minus the pKa of the base on the right. They're going to give you the same answer, it's just a different way of looking at it. Does that make sense at all?
So pKa of the base on the right minus left.
Yeah. So, for instance, yeah. So you can either look at it as the group that's adding. So you can say, all right, the pKa of this is 35, the pKa of this is 0. Or you can look at the actual base here. The pKa of this minus the pKa of this. Just to be safe, let's just choose something. Let's just choose something and stay there since this is being videotaped. So let's just do it based on I'm not going to ask for the exact numbers if I ask. I'm going to ask for trends. But what's the best way to get a trend than actually doing the math and knowing? So for instance, if we do this, the pKa of the base on the right minus the pKa in the base of the left, this will give us 10 to this base, 35, minus this base, HCl, let's call it 0. So this would be 10 to the 35. So this KEQ of this reaction is favored by 10 to the 35, 35 orders of magnitude. Conversely, in this case, so again the pKa of HCl, again it's sub-zero, but let's just call it 0 for easy math. The pKa of this is 4-ish, 4.5. And so then for this, the KEQ will equal 10 to the 0 minus 4 equals 10 to the negative 4. So, this shouldn't be surprising, right? For this equilibrium, as drawn, the product is favored, the starting material is favored over the product, right? So, in cases when the starting material is favored over the product, is your KEQ going to be big or small? It's going to be small. Is it going to be less than 1? Yes, it is. By definition, if the starting material is favored over the product in any equilibrium, the KEQ is going to be less than 1. And in this case, 10 of the 0 minus 4 giving us 10 to the minus 4. Is that less than 1? Absolutely. Whereas this, where the product is much more favored than the starting material, 10 to the 35 minus 0 equals 10 to the 35, that's a huge number, right? Meaning that this equilibrium is hugely favored. So in that case, if I said rank it in order of increasing k value from small k's less than 1 being first, and large k's greater than, large k's being last, then we'd say, all right, this is smaller, this is bigger. So we go ranking in order of increasing, 2, then 1. right? And so frankly, you don't need to do this analysis at pKa's. You know, if you know the rough idea, you can just rank it in your head. But, you know, it's just, I feel like you guys will have more peace of mind if you actually do this pKa analysis to rank the equilibriums. Yeah,
Are we gonna be given the PKs?
of course. I always give you guys pKa tables in the back of the exam. But it's always good to know some basic ones in the top of your head to save time. Like, so, you know, what's up?
Just for the equivalents for the means, it's 2 equivalents.
Yeah, 2 equivalents of a mean.
So it's always left minus right.
So, yeah, if you're talking about the actual nucleophile,
Okay.
it's left minus right. If you're talking about the group and the acyl group, it's right minus left. And so in my lecture, and I apologize, I was doing both. And I think that may have led to some confusion. So that's why right now I'm saying let's just stick to the developed KEQ. It's the base on the left minus the pKa of the base on the right of the leaving group. And I think that makes it a lot more simple and straightforward. Yeah.
What are we ranking again?
The KEQ. So how the reaction is favored towards the right. So the KEQ is another way of saying how far the product is favored over the starting material. If it's favored a lot, it's going to be a large K. If it's disfavored, it's going to be a K less than 1. Yeah.
Is it, what's the significance of the 2 equivalents of?
Oh, it's so what happens is when this adds and kicks up, it kicks up HCl. So if you only added 1 equivalent, only half of the amine would add. The other half of the amine would be protonated by the HCl and you wouldn't get full conversion. Just going over the mechanism just real quickly. So amine adds Tetrahedral Intermediate. Kicks off Cl. And this protonated amide is really acidic, so the chlorine is going to quickly take this proton, and so that would give us HCl. But if we form this HCl in theory, then when we wanted to do the next equivalent of this reaction with another equivalent of amine, its choice would be to add in or depronate HCl. What's going to be easier, an amine depronating HCl or adding to a carbonyl? Depronating HCl every day of the week. So then what would end up happening is, if you only added 1 equivalent, only the first half of the amine would add into the carbonyl, the second half would just become protonated and not be reactive. So in order for a reactor to go to full conversion, you need 2 equivalents of amine. Another thing you can do is you can add just some sacrificial lamb amine to act as a base. And that's actually what we really do. We add a tertiary amine that's really cheap called triethylamine. And triethylamine will soak up the proton for us.
Professor,
Yeah.
did that say 2 equivalents or 20 equivalents?
Oh, 2.0.
Okay.
So that's the first part of chapter 17, dealing with just the straight up swap. Nucleophile adds into carbonyl with leaving group falls off, and then you have to tell me where the equilibrium lies. From there, we went to something that was very, very important, which was ways to get around the equilibrium problem. And so, here's an example. Where would this equilibrium lie?
1 to 1.
Yeah, exactly, right? It would be roughly 1. pKa-wise, Methanol is 16, water is 15.7. So the equilibrium would be 10 to the 16 minus 15.7, which is 10 to the 0.3, which is not that big of a number. It's it'll slightly favor the product, but roughly 1-to-1. For all intents and purposes, it'll be 1-to-1. So how do we overcome the pKa issue when it's equal? And then the answer was, if you can activate the system using acid or base, you can do it. And so I showed you 2 reactions that you guys should know. First is, if you want to go from a carboxylic acid to an ester, the conditions you want to use are H3O and methanol. The most common acid used is HCl. HCl is the most common acid used for this, but you can really use any acid. I think in the lab you guys use sulfuric acid. But if you take H3O and methanol, and you use excess methanol, and that's the key, you need to use methanol as your solvent. Why, when we use methanol as a solvent, is the equilibrium shifted completely to the ester? Le Chatelier's. You have excess starting material, i.e. methanol as your solvent, so you have 10 times 10 to the, 20th equivalents of methanol or something ridiculous like that. The equilibrium is going to absolutely be shifted to the methanol. And so, because we're using excess methanol, Le Chatelier's is going to shift the equilibrium completely to the product. Mechanism, real quickly. Protonation of the carbonyl. To give us this cationic species, and since the carbonyl is now protonated, it's going to be much more electrophilic because it's got a positive charge in the system. So it's going to attack, giving us our favorite Tetrahedral Intermediate. All right. We can next have a proton transfer. But of course the proton transfer is probably going to have a KEQ of 1 because going from a proton on the methylated alcohol to a proton on one of the OHs is not going to, it's going to have no pKa driving force, so it's going to have a very, equal distribution. So let's have this oxygen take the proton. And so I like to do a lot of intermolecular proton transfers because it saves time. The one piece of advice I will give you is intramolecular proton transfers are good most of the time, but intramolecular, so within the same molecule like this, are good most of the time. Intermolecular proton transfers are good all of the time. So if you're not sure, just do an intermolecular. If it's a case like this where it's pretty obvious, then do an intra. But just realize that inter work all the time, intra work most of the time for a mechanism. That is some wisdom from one Tim Montgomery, who I apparently found out from his research advisor used to be a pro surfer. I haven't asked him to verify. I also didn't ask his research advisor what the definition of pro surfer meant, because I think there's various levels of being a pro surfer, right? So we get this protonated water, and we can kick it off. And that gives us a molecule like this. That's the protonated ester. And then we're swimming in water. No pun intended. It helped me swim in water. I don't know what else we can really swim in. And then we get our ester product. So again, this is the basic Fischer esterification mechanism. And I want to point out each of these steps is going to have a fairly equal equilibrium. So there's nothing that really drives this equilibrium forward, except for the fact we have a million zillion Google times excess methanol. Actually, I don't think we have a Google times excess because that's much larger than Avogadro's number. But still, we have a large excess of methanol, so that drives the equilibrium towards the product a la Le Chatelier's theorem. I'm going to have to tell Diane Smith how often Professor Smith, how often I use Le Chatelier's theorem. I think she'll be proud. So the other reaction I showed you with this that was key was going from a methyl ester to a carboxylic acid. A methyl ester to a carboxylic acid. Once again, pKa-wise, between a methyl ester and a carboxylic acid, there was no real driving force, right? It's not going to really favor either one. It's going to go and it's going to go back and forth. But because the carboxylic acid can be deprotonated under the basic conditions because it's so acidic, that will give us a carboxylate. And the fact that under basic conditions, the product carboxylic acid is deprotonated to the carboxylate, that drives the equilibrium. So this equilibrium is pretty lousy, 1-to-1. However, this equilibrium is going to be, so sodium hydroxide has a pKa of 16. This has a pKa of 4. So what's the KEQ of this equilibrium going to basically be? 10 to the 16 minus 10 to the 4, right? So 10 to the 12th. So whereas this will have a KEQ of 1 and have no real thermodynamic driving force, this will have a KEQ of 10 to the 12th. 10 to the positive 12th for this. And so what that means is this deprotonation is going to drive the equal. So the second we form this is going to be deprotonated to go here. And then Le Chatelier's is going to take over to bring this over to here to reach equilibrium, but really it's being tricked, because the second this is formed, it's going to be deprotonated again. So the equilibrium is completely being fooled by Le Chatelier's because of this protonation, if you want to think of it that way. So because we can do this deprotonation event, it's going to drive the equilibrium to the product. And of course, that came up when we were talking about the Claisen condensation as well, having this equilibrium driving event. And then this is just sodium hydroxide adding, giving us a tetrahedral intermediate, then kicking off the methanol, the MEO minus, to give us this, plus MEO minus. And of course, in this case, the carboxylic acid is swimming in sodium hydroxide and swimming in this leaving group. So one of these bases is going to quickly bogard the proton, if you will, and give us the carboxylate. I'm glad someone caught that. So this is saponification. In saponification, you'll take some fatty acid you get from somewhere, no questions asked, and you throw in sodium hydroxide, which in old times sodium hydroxide is lye. Lye is sodium hydroxide. So when you make soap, you take your fatty acid you get in Fight Club, they got it from a cosmetic surgeon, and you throw in your lye or your sodium hydroxide, and you get off a carboxylic acid plus an alcohol. In Same idea, yes.
If there's no methanol, we just assume that there's water because of the NaOH, right? Increase.
Yes, yes. Methanol is the solvent most people use. The reason most people like to use methanol rather than water is, well, if you're making soap, you just use water. So making soap, they just use water. But pragmatically, the reason people use methanol is because esters usually aren't that water soluble. Esters usually aren't that water soluble. And so you just get your salad dressing. You get your sodium hydroxide lye solution and your ester just sitting on top, and nothing happens. So if you use methanol, then methanol will be able to both dissolve the lye, sodium hydroxide, as well as dissolve the ester. And it occurs faster. But yeah, you can do it in water. You can make soap. I don't think Tyler Durden made it in methanol or anything. So that was a key part. Then we talked about other things like making acid chlorides using thionyl chloride. Don't forget that. But then the real key part, the other key part of chapter 17 was, yeah.
Sorry. So then you get the carboxylate.
Yeah.
The way to get the carboxylate, you have to add the H3O plus, right?
Yeah, so this is the classic kind of quasi-trick question that's not really a trick question.
Okay.
Is if I say H3O, then the answer is the carboxylic acid. If I don't say H3O, the answer is the carboxylate.
Okay.
It's really a question aimed to make sure you guys are paying attention. Along those lines, I've always toyed with the idea of having the first set of instructions say, this is a take-home exam, so please leave and turn in the exam on Monday.
Do it tomorrow.
Yeah.
I've always toyed with doing that, but then all my colleagues have told me it's a bad idea.
They're wrong. They're totally wrong.
Yeah. I'll try it out in my graduate, in my upper division chemistry class I teach next semester. Anyway, the other key part of chapter 17 was amide formation. Particularly, there was one key, and so to make amides, obviously you can take an acid chloride and an amine, or an acetic anhydride and an amine. But the key thing we showed you which is real modern chemistry that is still used to this day. In fact, this reaction, this DCC reaction, has probably been used in my lab 5 times in the last 4 days. So it's something that's really used a lot. Which is a carboxylic acid plus DCC plus your amine gives you the amide plus dicyclohexylurea and CY is just an abbreviation for a 6-membered cyclohexane. Sorry. It'll give us this, plus a lot of times we'll get about 5 to 10% of a side product. Where one of the nitrogens in the urea is actually acylated by the initial carboxylic acid. So the mechanism of this is first the amine, sp2 amine, and the DCC grabbing the proton. And I don't do this in lecture, but just to save time and space, I'm just gonna draw the resulting ionic pair here. So the DCC grabs the protons, and now we have our carboxylate with an O minus, and now we have our Iminium-like thing from the DCC. So first step is DCC amine taking the proton from the acidic carboxylic acid. And this rapidly sets up for the carboxylic acid to attack the carbon adjacent to the positively charged nitrogen.
Would it
Yes.
be wrong if we just the carboxylate attack the carbon first?
Well, we need to form the carboxylate. And so the product is carboxylic acid plus this, right? And so the carboxylic acid is not going to be nucleophilic enough to attack.
Okay, the book.
The book's wrong.
Okay.
I mentioned that in lecture. Every chemist I've ever shown the book's mechanism has had the same response I did when I looked at it, which was, what the F were they thinking? Pedagogically speaking, they were trying to make it as similar to a thionyl chloride reaction as possible. That's why they have their mechanism that way. It's wrong.
Okay. Thank you.
I've shown it to Professor Bergdahl, I've shown it to Professor Peirce, I've shown it to Professor Grochon. They don't teach 432. So they had never seen the mechanism. And then their response was kind of like, really? So it's wrong, yeah, the book's mechanism.
Does it matter which nitrogen the hydrogen goes to in the
No,
beginning?
absolutely not. They're equivalent. So I'm not going to say the book's wrong, because I know why they made the decision. Pedagogically, they were trying to make it similar to thionyl chloride. But it's one of these reasons when for pedagogically speaking, so to teach better, you actually maybe tell a small fib to the class about how something actually works. And I'm still young and naive and can't bring myself to do that. Yeah?
Is there something missing from the amine? Like if there's only two bonds to the nitrogen, it's supposed to be...
What you mean?
Sorry, the reaction.
This
The arrow.
Reaction product itself, like that, yeah, that.
are a nitrogen bound to the amide?
Straight to the left,
Should there be a hydrogen on the nitrogen?
yeah.
This nitrogen?
No.
On the arrow.
On the
It's
reactor.
on the arrow.
Oh, yeah, okay.
Delegate.
Yeah. Yeah, my bad. A lot of times I look at those as just inconsequential, things that are there just implied, but that's my fault. I should have had it there. Reactions still work. In fact, if this was to have the proton, it would be more nucleophilic, right?
Right.
But yeah, proton should be there. So we get this intermediate. The key thing about this intermediate is we go from having an oxygen like OH as a leaving group, which has a pKa of 16, to a urea as a leaving group, which is going to have a pKa of like 7 or 8. So we're making the equilibrium of the amine, adding to this, kicking this off, to be now favored, to be now significantly favored by another 6 or 7 orders of magnitude. So we took a bad leaving group and we made a good leaving group. And what I like to point out is this kind of reminds us of an anhydride, right? Kind of like an anhydride, so let's think of it as this step activates this to look like an anhydride. So we make this like an anhydride. And first off, let's talk about the side product first. The side product forms from this nitrogen doing an intramolecular reaction, attacking this carbonyl, and then kicking this off. So this attacking this tetrahedral intermediate, collapsing, kicking this off to give us the side product. So the side product forms, and I'm emphasizing this, and so take that for whatever it means, but the side product forms from an intramolecular reaction of the nitrogen in this intermediate acting as the amine and attacking it. It's in the mean, right? So it's sp2, so it's not going to be as nucleophilic, so that's why we only get 5% of it. But still, the way the side product forms is through this intramolecular reaction. I'm not going to draw it out, but it's just this attacking this and then doing the typical collapse, yeah.
So then for the actual product, it's what's on top of the arrow, does that same amine, but it would be intermolecular instead of intra?
Well, no, so for the product, it's actually this amine doing
Yeah,
it.
that amine,
Yeah.
that lone pair
Yeah, and
attacks
so,
in and does
yeah.
the same
So
thing.
instead of doing, so this lone pair of electrons will give the side product, whereas this lone pair of electrons will give the product. But the mechanism's the same, it's an amine attacking. So for this case, for the productive pathway, it's the amine attacking, giving us our tetrahedral intermediate. And then the tetrahedral intermediate collapsing, kicking off the anion of the urea. So as drawn here, what the next product we would have would be the protonated amide plus the leaving group, which was the anion of the urea. But of course, almost instantaneously, this anion is going to grab this proton and then give us our neutral product and then the urea. And that works, with the tetrahedral intermediate. There's some ambiguous with where the proton transfer happens. So if I were to draw, I'll draw this tetrahedral intermediate right here. Well, I'm like, was that some meme I'm missing?
The carbonyl takes off the oxygen.
Yeah.
Okay.
Yeah. So we form this tetrahedral intermediate. And so you could draw it directly like this, where we kick off the anion. I guess, and it's going to be in the other tautomer of this. I guess you could. Well, it's going to quickly tautomerize. But yes, no. So the oxygen, the way that the electron flow really is. Would be like this. So oxygen goes into here, kicking this off. This electron density goes to form an oxygen carbon carbonyl, and then this lone pair goes with a minus charge in the nitrogen. Of course, there will be tautomerization. And whatever tautomer you draw, I don't think it really matters. The reason I drew this though is so there's also another possible proton transfer, right? We could have this oxygen take the proton and then kick it off, or we could have this nitrogen and the leaving group take the proton and then kick off the neutral urea. Again, there's some ambiguity. I can talk right now, but It's a girl, no. There's some, there's a couple options. I think the options are all reasonable. And I think that when it comes to mechanisms, I think the TAs have proven that when it comes to something like a proton transfer, and there's 2 or 3, reasonable possibilities, they'll give you slack, whichever way you do, as long as it's chemically reasonable. But just, key thing is this tetrahedral intermediate and then it collapsing, so on and so forth. Yeah.
Well, that always be one of the products, the one of the blue ones.
If- You mean this guy, the side product?
No, the one on top of it. That will always be one of the products.
This guy?
Yeah.
Absolutely.
That's urea?
Absolutely, as a urea.
Professor,
Yeah.
can the neutral urea actually react with the carbonyl on the first reactant to make that side product, the 5%, instead of doing what you said earlier, where you circled in orange?
So the difference between that is that would be a inter-molecular reaction.
But
And
it's gonna go-
intra always occur easier than intra.
Okay.
And so the other thing is, so the nitrogen that attacks intramolecular to get the correct product, is an sp3 nitrogen. sp3 nitrogens are going to be much more nucleophilic than sp2 nitrogens because of the whole more S character being closer to the nucleus and being less reactive argument. And so it's going to be much more difficult for the urea to attack in an intermolecular way than an intra.
So it doesn't happen?
If it does happen, it's not going to be very significant.
If you draw it, though,
In general, the accepted way, and there's several mechanistic experiments that prove this, is that the side product forms through the intramolecular mechanism. The intra, not the inter.
But you said it happens like 1%, so if we draw it, are we still correct? That's what I want.
No.
So we're incorrect.
So if you have the urea attacking,
Yes.
no. Because the reason being the urea is going to be protonated pretty quickly, right?
Okay.
So it's not going to be reactive. And even if you did, it's sp2 nitrogens are a lot less reactive than sp3 nitrogens. And so if they have the intramolecular advantage, it can happen significantly.
Okay.
But if it now is intermolecular, so you have an sp2 nitrogen trying to react intermolecularly versus an sp3 amine trying to react intermolecularly, the sp2 is going to have no chance.
Okay.
The only time the sp2 can compete is when it's got this intramolecular home field advantage.
Okay.
Okay? Yeah.
So that would be the quote-unquote good amine versus bad, like you said?
Yeah, exactly. So usually when this side product forms, it's because you're using an amine that's not good for some reason.
Okay.
I found a lot of reasons why the amine wasn't good. Sometimes it's just not reactive, like it's really sterically hindered. So if you have a sterically hindered amine, it's going to be harder for it to attack. And so then you can have some of this forming as a side product because there's more time for it to be formed. One time, or 2 times, or 4 times, I may have forgot to add the amine. When you do a million of these reactions, it happens. And then you're like, why do I have all the urea? Oh, because I forgot. The amine I'm going to add is still on my bench top, laid out, ready to be added. Whoops. But yeah, it can happen. Yeah.
On that concern step, is that arrow forming a double bond or is it adding?
Oh, so this arrow?
Yeah.
The way I do it is forming a double bond.
Okay, so but isn't it supposed to be coming from
the oxygen?
blue? Because it looks like you had it drawn from that red line. It should be drawn from the blue bond right next to it.
Sapling has taught you guys well. Yeah.
Okay.
Although, I'll say good for Sapling, because Sapling's really picky with that stuff, right?
Yeah. It's okay.
Obviously, Sapling wasn't around when I took this class. But yeah, no, you're right.
And is it okay for us to draw that rather than drawing the tetrahedral
Yeah.
intermediate?
Yeah, I'm all for drawing this at the same time. There are some times where you might have, I'll say draw the tetrahedral intermediate, or the tetrahedral intermediate might just be key.
Okay.
But in general, for, I felt, we've talked about, if I ask you the mechanism of a Fischer esterification, the tetrahedral intermediate is kind of key, right? So you draw that. But for a lot of reactions, if anyone takes Professor Brigdall's 500 level chemistry class or my 500 level chemistry class, no one's going to ever ask you to draw the tetrahedral intermediate unless it's important. and Drong's considered thing is more than 5.
Thank you.
Wait,
Yeah.
so,
Underneath the product, you have an anion drawn. Where did you get that anion
This guy?
from? Yes.
Oh, this is, as I drew this tetrahedral intermediate, this kicks off the anion of the urea, which is going to quickly take this proton to go to here. So, as this is drawn, this stuff's going to leave originally as an anion, the anion of the urea. And then it's gonna, and so as this is drawn, this will give us the anion of the urea plus, plus the protonated amine, and almost instantaneously this anion's gonna grab the proton to give us the products in neutral form. Yeah.
Had there not been a carbonyl there, like had that not been urea, would it have been possible for the anion to leave? Or is that only possible because the nitrogen is stabilized by that carbonyl bond?
It's stabilized by a carbonyl bond. You need something that's gonna have a good low pKa. Yeah,
Any hints as far as synthesis problems?
any what?
Hints regarding synthesis problems or?
We'll see how we get, there are some synthetic questions.
Retrosynthesis analysis?
Yeah, but I think I tried to make them fairly reasonable. I tried.
Reminiscent of the practice exam, perhaps?
Similar difficulty.
Okay.
And then the really hard ones from last semester, I learned my lesson and changed accordingly. So I was talking about the practice exams, they were my first time teaching the class. And so it's just, you know, you kind of learn, you learn what's too hard and you learn what's too easy, and then the next time you teach it, it's kind of a better balance. And so I'll admit I had some synthesis questions that I typed to TAs, and the TAs would get it instantly, and then I thought, oh, this is great. And then you realize actually there are some subtleties that aren't as obvious to, you know, newer students. So I made it a point to try to stay away from those. You know, but you know, understanding, if you can understand the synthetic, what I'm trying to say is, if you can do the synthetic problems on my practice exams and the final, you'll be fine forever, I ask. And we'll get there shortly. Right now I'm just trying to do something different and then just go through kind of what we're covering. So then after this amide mechanism, then that's when we went to chapter 18. And the key of chapter 18 was enols and enolates. And this is after spring break, right? So I just went through everything before spring break, right?
Yeah.
All right, so you guys want me to go over the more recent stuff since spring break, or do you want me to start taking questions?
Yes.
Just keep on going.
All right, how many want me to keep on going?
Yeah.
All right, I think the ayes have it. So my wife goes and told her mom. And I guess her mom must think I'm the weak link because she keeps texting me asking.
Are you gonna tell her that you told us what it was first?
Of course.
And then the YouTube.
Yeah, true.
It's in here somewhere.
So that takes us to Enolate Chemistry. And so the two key, in the beginning of the chapter, the key concepts are the fact that hydrogens on carbons alpha to carbonyls are surprisingly acidic, pKa 20 to 24,